Hi everyone, welcome to the Chapter 16 lecture on air quality. We're going to be talking about the atmosphere, pollution in the atmosphere, categories of pollutants, photochemical smog. We're going to skip acid deposition. We will talk about ozone depletion, control of air pollution, and air pollution in the developing world. I do want you to read through the sections in your textbook on acid deposition, and I'm also omitting from the lecture some sections on indoor air pollution. So read through those bits in your textbook, but they're not going to be the focus of this lecture, all right? So our atmosphere is composed of gas, right? And no surprise, most of our atmosphere is nitrogen. Oxygen makes up about 23%, and there's some other gases that contribute there, like argon, carbon dioxide, and some other minor contributors. The atmosphere is made up of 4 layers. So starting down at the surface of the Earth, we breathe troposphere. Above that is the stratosphere. This is where the ozone layer is that protects us from UV radiation. Above that is the mesosphere, and then above that is the thermosphere. As air absorbs heat from the earth, it expands and rises. And when the heat content of the air radiates into space, the air cools and becomes more dense and flows back down towards Earth. That causes a circulation of air that forms a pattern like this. Warm air gets heated by the earth and rises. As it rises, the air cools and sinks back down. So that forms areas of high pressure, where there's cool air that sinks, and low pressure, where warm air is rising. The combination of all air movements creates the wind and the weather patterns characteristic of different regions in the world. Keep in mind that as air is circulating vertically, it also moves horizontally as the earth spins underneath it on its axis, which leads to some really cool patterns like this. So the earth spins from east to west, right? So the earth is spinning this way. And that means that the general flow of air underneath is going to be moving at the same direction along the equator. So I want you to think about which way the earth spins and how does that relate to the wind patterns that we see here in this image. Air pollution is directly related to the number of people living in an area and the kinds of activities that those people are doing. In urbanized, industrialized societies, there are dense concentrations of people that use large quantities of fossil fuels for manufacturing, transportation, and domestic purposes. These activities release large quantities of polluting byproducts into the environment. Many of the megacities of the developing world have extremely poor air quality, and the causes of this pollution are open fires, poorly maintained motor vehicles, and poorly regulated industrial plants. The World Health Organization estimates that air pollution accounts for about 7 million deaths annually, and 20 to 30% of all respiratory disease appear to be caused by air pollution. Have a look at these 2 graphs. The one on the left is population density for counties in the US and Puerto Rico. So the darker the color brown, the more densely populated the area. So looking at this map, now take a peek over here at this one. This is a daily peak air quality index. So the warmer the color, the lower the air quality, right? And there's definitely a strong relationship between highly developed areas and poor air quality, right? In the East Coast, over here. Air pollutants are sorted into categories, and the 5 major types of materials that are released directly into the atmosphere in unmodified forms in sufficient quantities to pose a health risk. These are called primary air pollutants, and they include carbon monoxide, volatile organic compounds, or VOCs. Sometimes they're also called hydrocarbons, particulate matter, sulfur dioxide, and oxides of nitrogen. Secondary air pollutants formed by reactions of primary pollutants and water or sunlight. These are things like ozone. Criteria air pollutants are those pollutants for which specific air quality standards have been set by the United States Environmental Protection Agency. They include nitrogen dioxide, ozone, sulfur dioxide, particulate matter like dust, carbon monoxide, and lead. Certain compounds with high toxicity are known as hazardous air pollutants. So here's a list of air pollutant standards. And I'm not going to go through this list with you in the lecture, but what I'd like you to do is pause the video and study the list for a minute. These are air pollutants listed on the left, and there's 3 different standards here. There's the United States National Ambient Air Quality Standards, European Union Air Quality Standards, and the World Health Organization's Air Quality Guidelines. And you'll notice they're not all the same. Like for nitrogen dioxide, in the US, we're permitted to have levels up to 100 micrograms per cubic meter, whereas in the EU and the World Health Organization, they recommend no more than 40 micrograms per cubic meter. So have a look at these 3 columns here and see how they compare. Are there any patterns? And record those in your notes. Carbon monoxide is produced when organic materials are burned with insufficient oxygen. This is the single largest source of carbon monoxide in the atmosphere is from an automobile. So 50% of vehicles, 50% of the carbon monoxide is from vehicles driven on roads. Vehicles like ATVs that are not used on roads or farm equipment are also a significant source. And the remainder is from burning, like in power plants or burning leaves, anytime there's combustion. And the carbon monoxide binds to hemoglobin in your blood. And this is what can make it so deadly. When carbon monoxide binds with the hemoglobin in your blood, it makes your blood less able to carry oxygen. And it can be incredibly dangerous in enclosed spaces. After just several hours of exposure to air containing only 0.001% carbon monoxide can be enough to kill you. So it's very dangerous if you have natural gas or propane burning appliances in your home, including your furnace. Then you should have one of these, a carbon monoxide alarm. So if you don't have a carbon monoxide detector in your home and you do burn natural gas or propane, like maybe in your dryer for your clothes or your oven or your furnace, make sure that you have one of these. And I think you can even get some that are both a smoke alarm and a carbon monoxide alarm. Carbon monoxide gas is clear and odorless. So if you were to have a leak in your home, or a buildup of carbon monoxide, you might not know it until it's too late. And usually the symptoms people experience are they're like groggy and they can't think clearly and they're very sleepy. Well, thankfully, this is a very rare problem, but still one that's worth investing the $20 in an alarm. All right, so cigarette smoking is an important source of carbon monoxide. The person's directly inhaling that carbon monoxide. It's not a persistent pollutant though. So it combines with oxygen in the air to form carbon dioxide. And air can be cleared of its carbon monoxide if no new carbon monoxide is introduced. U.S. levels of carbon monoxide have declined by about 74% between 1990 and 2018. And all areas of the U.S. meet the standards now set by the U.S. EPA. Particulate matter consists of tiny solid particles and liquid droplets dispersed in the atmosphere. The EPA has set standards for 2 kinds of particulates. There's coarse particulates, and we'll call those PM10, that are between 10 and 2.5 microns. There's also fine particles, and those are particles that are smaller than 2.5 microns. Most PM10 particles are primary pollutants released directly into the air, like dust and smoke. Most PM2.5 particles are secondary pollutants, things like sulfates and nitrates. Particulates can accumulate in your lungs and interfere with the ability of your lung to exchange gases. The amount of PM10 has decreased by 26%. From 1990 to 2018. And the US EPA has been setting PM 2.5 standards for a shorter period of time. The amount decreased by 39% between 2000 and 2018. Most communities now meet the standards for PM10 and 2.5. Sulfur dioxide is a compound of sulfur and oxygen produced when sulfur-containing fossil fuels are burned. Burning coal releases sulfur dioxide, and so coal-fired power plants were a major producer of this pollutant, and they were required to reduce emissions by the EPA. Utility companies have shut down many coal-fired power plants, and U.S. levels of sulfur dioxide have decreased by 89% between 1990 and 2018. Nearly all communities meet the sulfur dioxide standards set by the EPA. And most areas that do not meet the standards are associated with coal-fired power plants. Here's a picture of a coal-fired power plant. All right, nitrogen dioxide. Oxides of nitrogen, or NOx. This X is just a variable, a placeholder. And it can be replaced by a 1, a 2, or N2O. These are all different types of nitrous oxides. The nitrogen and oxygen molecules in the air combine with one another when subjected to the high temperatures of combustion. Nitrogen monoxide and nitrogen dioxide are the most common oxides of nitrogen. And burning fossil fuels and internal combustion engines, like those in vehicles, is the primary source of nitrogen oxides. Cars produce 35%, non-road motorized equipment produces another 20%, and power plants produce another 20%. About 75% of the nitrogen monoxide produced by an automobile engine is converted back into N2 and O2 by the catalytic converter. An increase in the number of cars and miles driven offsets the gains attributed to catalytic converters, however. And there's been about a 57% reduction in nitrogen dioxide emissions from 1990 to 2018. All communities meet the EPA standards for nitrogen oxides now. And nitrogen oxides still remain a problem, however, because they contribute to the development of photochemical smog. And this is a picture down here of a catalytic converter if you've not seen one. Lead. Lead can enter your body through breathing airborne particles or consuming lead deposited on surfaces. Lead accumulates in your body. It's a heavy metal and can cause mental retardation and kidney damage. Leaded gasoline was the primary source of exposure for people in the U.S. historically. Almost all countries have phased out lead as an additive to gasoline. And in the U.S., lead emissions peaked at about 258,000 tons per year. In 2014, they were down to about 730 tons per year, a reduction of 99.7%. Nearly all areas meet EPA standards in the U.S. Volatile organic compounds, or VOCs, are organic compounds that are readily evaporate and become pollutants in the air. These are things that they evaporate fast and they're smelly. So since they're composed primarily of carbon and hydrogen, they're often referred to as hydrocarbons. Sources of VOC air emissions include industry activities and internal combustion engines. VOCs are important in the processes that lead to the production of secondary air pollutants found in smog. VOCs are regulated indirectly because they contribute to the production of ozone that is regulated. An emission of VOCs decreased by about 42% between 1990 and 2018. And here's some examples of some common household VOCs. Things like Drano, lacquer thinner, wood finish, Krylon, paint thinner, all these kinds of like really smelly chemicals. All right, ozone. So ozone, or O3, is a secondary air pollutant when it's formed as a product of photochemical smog. Ozone is highly reactive and causes health problems as a result. Ozone is difficult to regulate, and it's only been reduced by about 20% since 1990. Many localities periodically do not meet ozone standards, and about 122 million U.S. citizens live in areas with periodic ozone problems. So if you look down here in the troposphere, this is where smog is formed. This is a bad place for ozone to be. So when ozone is present down in the troposphere, it's a pollutant and it causes health problems because that's where we live and we're breathing it. Good ozone belongs up in the stratosphere. That's where the ozone layer is that helps to protect the surface of the Earth from harmful UV radiation. So ozone is good if it's up in the stratosphere where it belongs. But when it's formed artificially by human activities down here in the troposphere where we live, then it's a problem. It's important that you understand this distinction. In 1985, it was discovered that a significant thinning of the ozone layer over Antarctica had occurred during the southern hemisphere spring. This area became known as the ozone hole, and ozone in the outer layers of the atmosphere helps to shield the Earth from the harmful effects of ultraviolet light radiation. And one of the biggest ways we see that impact on our own human health is skin cancer. Chlorofluorocarbons, or CFCs, and similar compounds release chlorine atoms, which can lead to the destruction of ozone. It can take 10 to 20 years for those CFC molecules to get to the stratosphere, where the ozone layer is. CFCs can remain in the stratosphere and react with the ozone for up to 120 years. There's some significant time lags and persistence there that we're just going to have to be patient and make sure we're not contributing more to, right? Actions to protect the ozone layer. The Montreal Protocol was an international treaty established in 1988, and initially it limited the production of CFCs and halon, which is used in fire extinguishers, at 1988 levels. So in 1988, countries got together and kind of agreed, like, okay, no more. We're going to keep it. We're capping it where we're at right here. It further called for production of CFCs to be reduced by 50% by the year 2000. And ultimately, all production of CFCs and halon was stopped. This was ratified by our Congress in 1988, and emissions of CFCs have dropped dramatically. And it appears that the size in the ozone hole may be stabilizing or even getting smaller. So this image here, I have a picture of the ozone hole in the southern hemisphere. Basically, the concentration of ozone is higher the warmer the color. And it is lower the closer you get to purple. So there's a big giant spot in the ozone down here that has 200 or less Dobson units of ozone. So it's very thin or absent entirely. Compare that to what the ozone looks like in the northern hemisphere. We can see there's a lighter patch forming, but it's not a complete hole yet. So hopefully things are on the mend. And you can look at this graph here. It shows the change in the size of the Antarctic ozone hole over time. So starting in 1980, and then following it through time up to 2020. And there's even some hope that this downward trend from 2015 is real and that the size of the ozone hole is actually shrinking. But time will tell. Hazardous air pollutants. These are the majority of air toxics, and they're released as a result of manufacturing processes. Things like perchloroethylene released from dry cleaning establishments, toxic metals released from smelters, chemical and petroleum industries are the primary sources of hazardous air pollutants, and people exposed on the job are the ones most likely to be harmed. All right, photochemical smog forms from the interaction of nitrogen dioxide, nitrogen monoxide, VOCs, and sunlight in a warm environment. And this smog is a mixture of pollutants. And the word smog itself comes from smoke and fog, right? Photochemical smog involves the production of secondary air pollutants. So when these things get together, and it's warm out and there's sunlight, then we have the production of secondary air pollutants. Here's a picture of photochemical smog. It's usually got a little bit of an orangey cast to it from the nitrogen. And how does this smog form anyways? So photochemical smog has several ingredients that are required. We have to have nitrogen oxides and VOCs. We have to have sunlight and warm temperatures to promote those chemical reactions to produce the secondary pollutants. And in most urban areas, nitrogen monoxide, nitrogen dioxide, and VOCs are present as byproducts of burning fuel in vehicles and industrial processes. And you can see here where there's a layer where the smog is sort of stuck down here in the city and it can't rise and escape and blow away, right? It's trapped there. So, how does photochemical smog actually work? What I want you to focus on as we talk through this table are the sources, the ingredients, and the products. The chemical reactions I will not quiz you on in this class, but you do need to know that they occur, okay? So the source is combustion. So people on their morning commutes, driving their cars, riding bus. We have combustion, and that produces nitrogen monoxide. Nitrogen monoxide reacts with oxygen and produces nitrogen dioxide. And this is a reddish-brown gas with a strong smell. Kind of like what those pictures look like, right? Sunlight has to be present. We have vehicle emissions also formed in the atmosphere from nitrogen oxide. So, we have nitrogen oxide that's going to react here with oxygen and nitrogen oxide. And ultimately, it's going to free up these oxygens in the form of ozone. Ozone is a problem for your respiratory system and an eye irritant. It injures your lung tissues and even the leaves of plants. And this, we're talking about ozone down in the troposphere, down in the air that we're breathing, right at the surface of the earth. And then vehicle use also produces VOCs, also known as hydrocarbons. And these hydrocarbons are going to react with hydroxides and oxygen, and they form highly reactive organic compounds. Those react with nitrogen dioxides and produce these PAN chemicals. So PANs are produced when the nitrogen oxides get involved, and they form peroxacetyl nitrates, or PANs. These are respiratory system and eye irritants. The highly reactive organic compounds are called aldehydes, and they are also respiratory system and eye irritants. So you can imagine that being down in this city, breathing the smog, is a really uncomfortable, unhealthy place to be. Smog is usually not omnipresent all day. It usually begins to form in the morning when people are doing their morning commute. So we're releasing the volatile organic compounds and those nitrogen oxides. These things are going to react together as the weather warms up and the sun comes out, and they're going to produce these secondary pollutants, the aldehydes and the ozone. And those are also going to peak here. And then as the day goes on, the sun begins to set, temperatures cool, things begin to sort of clear off throughout the day, but this is a predictable daily problem at certain times of the year in certain parts of the country or world. So climate and geography have a role to play with this. Cities with warm climates and lots of sunlight are more prone to develop photochemical smog. Warm temperatures and sunlight encourage those chemical reactions. Smog is more likely to be a problem this summer with higher temperatures and longer days. And cities adjacent to mountains or in valleys tend to have trouble with photochemical smog because the pollutants are trapped by thermal inversions. And a thermal inversion occurs when warm air becomes sandwiched between two layers of cold air, and it acts like a lid on a valley. Warm air can't rise, and that causes the smog to accumulate. So if we look here in a normal situation, pollutants are produced in the city by people. Air at the surface is warmed by solar radiation. That warm, less dense air rises and mixes with cooler air above. When it cools, it sinks back down, gets warmed up, rises back up. This is the same little flow of air currents that we talked about earlier in this lecture. And eventually pollutants are dispersed and they get blown out by that mixing. However, when a thermal inversion occurs, cool, denser air flows down the mountains into a valley or slides in from above the ocean. Then we have the arrival of dense, cool air that pushes the less dense warm air up, but there's still a cool, dense surface of air above that warm air that's not mixing because it's just been displaced, right? And that allows pollutants to accumulate, and it can't blow away. It can't get out of the valley. And the same thing can happen here in a coastal city where we have cool, dense air flowing in from the ocean, and it's kind of compacting and trapping all of the warm air and pollutants in the smog between a coastal range of mountains and the coast of an ocean itself. So a question I have for you is, are thermal inversions a problem just in places like California, or is that something we could see here? And the answer is that we can see it here. How long ago was it? Maybe 10 years ago. We lived in Bay City and I was working at Dow, and I was driving in my car for the morning commute from Bay City to Midland, and I could see a thermal inversion where the stacks of Dow were releasing, I don't know exactly what was in those smokestacks, but they're releasing their industrial air waste, and it was going up a little bit, but it was trapped and it was staying all down low. It was really shocking to see. So we can have thermal inversions occurring here, although generally photochemical smog is not something that we typically see in our part of Michigan. Excuse me. All right, the Clean Air Act. The original Clean Air Act came about in 1970. It's been amended a couple times since. And the EPA has a number of responsibilities under the original act of 1970 and its amendments. The responsibilities of the EPA under the Clean Air Act are to establish air quality standards and develop strategies for meeting those standards, They need to conduct periodic reviews of the criteria for air pollutants. They need to reduce emissions. They need to reduce air pollutants. And they need to ensure that sources of toxic air pollutants are reduced. The EPA needs to limit the use of chemicals that damage the stratospheric ozone layer, the good ozone. Implementation of the Clean Air Act and its amendments by the EPA led to the establishment of a series of detailed control requirements to meet the goals. These include all industries are required to obtain a permit to release material into the air. All new and existing sources of air pollution are subject to national ambient air quality standards. Any newly constructed facilities are subject to more stringent control technology and permitting requirements than pre-existing facilities. So every new facility that's built has to be better than the old ones that are being phased out. So over time, we should see a significant shift in how much air pollution these places are releasing. Hazardous air pollutants need to be specifically identified. Power plants are allowed to sell their sulfur dioxide release permits to other companies, and the net result of this program has been a rapid reduction in sulfur dioxide emissions. A program for the phase out of ozone depleting substances like CFCs, halons, carbon tetrachloride, and methylchloroform were established. And in 2007, the U.S. Supreme Court ruled that greenhouse gases like CO2 could be considered pollutants, and that gave the EPA the authority to regulate them under the Clean Air Act. In 2011, the EPA established new regulations on the release of mercury and several other toxic substances. And the improvement in air quality since the enactment of the Clean Air Act is a major success story. As a result of implementing the requirements of the Clean Air Act, a variety of pollution control mechanisms were employed, and air quality has improved significantly nationwide. So some actions that have reduced air pollution, a big one, is reducing motor vehicle emissions. So cars now are required to release less carbon monoxide, VOCs, nitrogen oxides, and ozone, which is a secondary pollutant formed by these things. Placing controls on emissions from motor vehicles has resulted in a significant improvement to air quality. And this is a picture of the Chevy Volt, Chevy's electric vehicle. Some other actions that have reduced air pollution are particulate matter emissions. These come from a variety of sources. Road dust is actually a major source of PM10 particles. Many industrial activities involve processes that produce dust. Mining and other earth-moving activities, farming, transfer of grain or coal from one container to another. Forest fires produce a lot of the fine particulate matter. And burning of fossil fuels is another major source. We have reduced particulate matter emissions by about 40%. Power plant emissions are another area where we've made a lot of headway. The primary pollutants associated with electric power plants are particulates, sulfur dioxide, and nitrogen oxides. Most PM10 emissions have been controlled with filters or with other mechanical means. The control of sulfur dioxide requires some fundamental changes to the way electricity is produced. And the EPA approached this problem by setting limits and allowing electric utilities to decide which options are best for them. Nitrogen oxides are produced whenever high temperature combustion occurs with air, and control of the release of nitrogen oxides typically involves processes that are technical and expensive. Emissions of particulates, sulfur dioxide, and nitrogen oxides from power plants have been reduced significantly. And here's a nice visual to show you. So these are U.S. improvements in air quality from 1980 to 2018. So they all start at 100%, right? Because that's 100% is just whatever the 1980 level was. But you can see for all of these different pollutants, the trend is the same. Once we begin to regulate and set limits, the amount released drops substantially. Like the amount of lead released now is almost zero. That's huge. Here's a map of world air pollution. So cooler colors like blues and greens have low annual mean particulate matter. So this one is just a graph or a visual of particulate matter pollution. The warmer the color, the more dust or particles there are in the air, the dirtier the air is, right? What I want you to do is pause the video, take a moment to study this graph or map. What patterns do you notice with air quality in developing versus developed nations? All right, in summary, the atmosphere has a tremendous ability to disperse pollutants. Carbon monoxide, hydrocarbons, particulate matter, sulfur dioxide, and oxides of nitrogen are the primary air pollutants. The U.S. EPA establishes standards for 6 pollutants known as criteria air pollutants. They include carbon monoxide, nitrogen dioxide, sulfur dioxide, VOCs, ozone, and lead. Chlorofluorocarbons, or CFCs, also lead to the destruction of ozone in the upper atmosphere, which results in increased amounts of UV light reaching Earth. All right, as always, if you have any questions, please write them down, bring them to office hours or to class.